All right, in this lecture, we're going to continue looking at ways of determining information about a function given its rate of change. Now, before we get started, I want to give this, I want you to pause the video and try this example. If we were in person in class, I would give this as a warm-up. This is something that you already know how to do. The first two parts are basically you're given a displacement function. So you're given, how far you are from some reference point over time, and you want to graph the velocity. All right, so you're taking the displacement and you're graphing velocity. So the velocity is the rate of change of the displacement, and so you're going to look at the slope of the displacement function in order to get information about the velocity. That's the first two parts of this, is to look at these displacement functions. And then I'm giving you, in part C, I'm giving you a velocity function and asking you to try to graph the displacement. So pause the video, give this a try, and then I will go through it with you. All right, so in this example, in part A, we're just given a graph of distance or displacement versus time, and we're asked to graph the velocity. Okay, so what I need to do, remember the velocity is the rate of change of displacement over time. So what I need to do is look at the slope of this curve, and this it's kind of a piecewise linear curve, but I'm just going to look at the slope in order to graph the velocity. So if you look at this first segment from 1 to 2, now if I look at some points here, it kind of looks like my slope is down 1 or down 2 and over 1. So I'm going to say that the slope here is -2. So slope equals -2. All right, which is the velocity. So I'm going to come over here and I'm going to graph the velocity. Now it's constant, right? Because the slope is constant of this section of the graph, and so over the first 2 seconds, the velocity is just a constant -2. I don't even know what the units are. Meters per second, feet per second, miles per hour. I don't know. All right. All right, so there's the graph of velocity for the first 2 seconds. All right, now between 2 and 4, right, it looks like it's just 0, or we're not going anywhere. Our distance isn't changing at all. Our displacement isn't changing. So between 2 and 4, we're stopped, right, which means that our velocity is 0 for that 2-second period. So I'm just going to kind of connect this up. But for that 2-second period, our velocity is 0, right? Because we're at the same position. We're at the same point, the same displacement over that whole period, right? So our velocity is 0. All right, and then you can see now in this section of the curve, it looks like it looks like I can go up over 1 and up 3. Right? So it looks like the slope here is 3. Okay. So from 4 to 7. From 4 to 7, we have a constant positive velocity of 3. Okay. And so we can graph it like that. And then suddenly we change, right? And now our displacement from whatever our reference point is decreasing. So we're headed back toward our reference point. All right. So between let's see, it looks like 7 and 10. It looks like we have it's constant slope, and the slope here looks like it's back to -2, right? Because if I go over 1 and down 1 to the next point, over 1 and down 1. So here the slope is another -2. Okay. All right, so now we're back down to -2 here for the last 3 units of time. All right, so I can connect this up just to so you get a sense of the curve here. So there's our velocity curve for the for this first function. All right. Now, if you take a look at this next one, you can see that we basically have the same slopes. Now, our whole graph has been shifted up, but we basically have the same slope. So if I look at this slope, I can see that it's a slope of -2. Here the slope is equal to 0 in this section here. This is a slope of 3 in here, and then over here the slope is again, slope is a -2. So if I graph that, it looks just exactly the same as what we got before. Okay, so it's -2, then it's 0 for a couple of seconds. It increases to +3, and then we come back down to slope of -2. Okay. Now notice that both of those curves look exactly the same. Both of those velocity curves. These two velocity curves look exactly the same for different displacement functions. Okay. So now these displacement functions look very similar, but they're not the same because one is shifted up. One's starting at 4 and then going, our displacement is initially a +4 from our reference point. And then we go to our reference point for a couple of seconds, and then we travel away from it, and then we start traveling back toward it. All right. So this one, it's kind of the same sort of motion. It's just that it's all shifted down, I guess, by 4 units. Okay. So the thing to notice though is that you have two different displacement functions that give you the same velocity curve, which has an impact on, when we talk about, we want to get information about a function from its rate of change. It's not necessarily going to be a unique function, and that's what I'm trying to illustrate with this example. So in this part C, we're given a velocity function, right, which is the derivative of displacement, d prime of t, all right? And now we want to graph the displacement curve. Okay, we want to know the distance traveled from the reference point. All right, well, so this is telling us the slope of the curve, but we don't really know where to start. But let's just say that we start at 0, 0. Okay, our initial distance, we're starting at our reference point. And then it looks like our slope is a +4 for 2 seconds. So over the first second, I'm going to travel 4 units. Over the next second, I'm going to travel another 4 units. And so over the first 2 seconds, or first 2 time units, whatever that time units happen to be, I'm going to just get my displacement is just a linear function over time. Right? It has a constant slope because my velocity was constant over that time period. Then the velocity drops down to a +1. Okay, so it's still positive, so we're going away from our reference point. We're just going away in a little more slowly. So we have a velocity of 1 for 2 seconds. Okay, so now so after 1 second, I'm going to be I've gone 1 unit, another 1 unit, and so now that portion of the curve looks like that. Okay, again, it's just a line with a constant slope because my velocity was constant, right? And the velocity is the slope of the displacement curve. All right, now we're suddenly traveling in the negative direction. Okay, so we have a -2. Our velocity is -2. Okay, so that means the slope of our displacement is -2. So, and it looks like we're doing that from 4 to 9. Okay, so I have to go down to over 1, right? So I'm going back towards my reference point by 2 units every second. Okay, so I can plot what some of those points are between 2 and 9. So you can see that, okay, at 9 seconds, I'm back to where I started from. So I can just connect up those points, and you can see, if I can draw a straight line, decently straight line. Okay, so that's supposed to be a straight line. Okay, because I have a constant velocity, which is the slope. So velocity is the slope of the displacement curve. And then suddenly in the last second, I'm going, I've suddenly changed course, and now I'm traveling in the positive direction. And I'm going at, the slope of, or the displacement is going at 2 units per second, or 2 units per unit of time. Okay. All right. So my slope is a positive 2 here. Okay. Over that last second. All right. So there is a graph. There is a graph of distance versus time. The key thing to remember is I had to make an assumption right off the bat that I was starting at 0, 0. But I may not have been starting at 0, 0. I may have been starting at, say, let's say 2, or let's do 4. Okay. If I started at 4, I mean, the shape of the curve is going to look the same, but it's so the slope here is going to be the same. So over the first second, I'm going to go 4 units because my slope is 4, and so the velocity is 4. And then the next second, I get kind of off the graph here, but you can see I'd probably be here. So over that first 2 seconds, I just have a straight line. And then again, I'm going to go 1 unit per second, or my velocity is 1. So that means the slope of the displacement graph is 1 over the next 2 seconds. And then I'm going to have the same slope, right? So the velocity is the same. So the slopes are the same. But you can see the curve is just shifted up by 4 because I've assumed that I'm starting at 4. So every one of these points is just increased by 4 units. So I'm going to have a curve that looks like that. Let's see. And then I've got to go down to here, I think. And then I'm going to jog up. Okay. So that's another possible graph for my displacement function. And the only thing that's different is I started at a different point. So I could also start 2 units behind. I could even graph one that's 2 units behind the reference point, and I would get another possible distance or displacement function. Okay, so then I would be, let's see, just gonna kind of put in some of these. Everything will just be shifted out by 2 units. Okay, so anyway, I'll try to sketch this in to kind of get the idea. You get the same. Oops, you get the same shape. Oops, it's just shifted up or down. All right, so in this last question, it just is asking: is the curve or the graph of the displacement in part C unique? And obviously, we already kind of covered that. No, it's not unique. It depends on the starting point. All right, and but if we have some information on any one point, if we know the distance or the displacement at any one point in time, then we can anchor it and we can come up with a new unique solution. So the main point of this example is just that if you're given information about the rate of change of a function and you're trying to figure out what the original function was, that function is not going to be unique unless you're given some idea or some point to anchor it, and then you can get a unique solution. But in general, the solution is the original function that you can get from the rate of change function is not necessarily unique unless you have some additional information.